All right, so the first thing that we're going to talk about today is the transimpedance amplifier. And a feedback transimpedance amplifier converts an input current signal into an output voltage signal, which means that we have a parallel connection for our feedback network, both at the input of the amplifier and the output of the amplifier. So for our basic open loop amplifier portion, as per usual, characterized by its input resistance R sub I, over which our input voltage VI occurs. We have our input current I sub I. My phone, don't know anybody from Sunnyvale, California, so they can leave me alone. Here's A, I, or not, like so. So here's our open loop amplifier. I have to remember if I've been putting a blue box around it or a red. And then below this, we will include our feedback network. Our feedback network is going to be injecting current into the input stage. So we're going to have a dependent source that is a current source like so. On port 1 of our feedback network. And then over here on port 2 of our feedback network, because we have a parallel connection, we're going to have an open circuit voltage. All right. And as I mentioned a little while ago, we're dealing with a parallel connection on both sides. So for our output of our network, here we're going to see V out. Like so. Looking in through this open circuited set of terminals is how we determine our output resistance with feedback. And then we have a parallel connection on the input side as well. Here's our current IF. Here's our signal current IS. And looking in here is where we see our input resistance with feedback. So this is our ideal case. And we should observe, we're going to skip the analysis that leads to this, that our gain with feedback AF is 1 plus Ka. Our input resistance with feedback, RIF, is our open loop input resistance divided by 1 plus Ka, because when we have a parallel connection, it lowers the resistance. And our output resistance with feedback will be RO over 1 plus Ka. So a parallel connection on both sides causes both our input resistance to go down and our output resistance to go down. For the practical case, we really just need to know how our feedback network behaves, right? How it's going to load our system. So to determine the quantity R11, we have our feedback network. Here is port 1. Here is port 2. We will find R11 by looking into port 1 with port 2 short-circuited. Effectively exactly what we did for our feedback voltage amplifier. So whenever we saw that our connection to port 2 was in parallel, we short-circuit it when we look in. To determine R22, we're going to do the exact same thing, but in the opposite direction. Bless you. So R22 is determined by looking into port 2 with port 1 short-circuited. And then to determine our feedback factor K, we have our feedback network. Here's port 1. Here's port 2. We apply a voltage source at the output, and we measure the feedback current at port 1 under the constraint that the voltage drop over port 1 is 0 volts or short circuit. So K is the ratio of IF over V out when we hold the voltage drop over port 1 to be 0. Right? So these are our quote unquote rules for determining our feedback factor and then seeing how our feedback network loads our trans resistance amplifier. Gregory, can I clarify something for you? V1 is equal to 0 volts. Effectively saying in order to calculate our feedback factor K correctly, we need to short circuit port 1. Any other questions, comments, or clarifications needed? All right. Example problem time. So let's say that we have this fellow. We have some resistance here, RD1. Some resistance here, RD2. Here's our output voltage terminal. DC bias voltage like so. And then we're going to link our output terminal to our input. By a resistor RF. And then our input signal I sig is here. So what does our feedback network look like? Well, so let's look at something here that might help us out a little bit. Okay. So in our ideal diagram, we can see effectively that our signal current IS flows into this node and branches off such that some portion of it flows into our amplifier, and the other portion branches off and flows through our feedback network. So I'm going to call this current here II, and this current here IF. Does this help clarify what our feedback network is? Look. This current I sig is our input to the system. This current that's branching off II is the input current to the open loop amplifier portion. And then II or IF is the current that's returned by the feedback, or the current that's taken away.
Is IF the same as AV out?
Yes, so the reason why we're not doing specific, so let me scroll back up here. Yeah.
Oh, I didn't see the IF.
Yes. So the IF is literally the IF. This is the representation for an ideal case. The resistor network isn't an ideal case because this feedback network will not actually load our open loop amplifier, and we're trying to figure out how our feedback network does. So we're looking for the connection effectively from the positive polarity terminal of where we measure voltage V out, which for our amplifier is literally the V out terminal, to where it connects to IF, which is simply the resistor RF like this. Where this is port 1 and this is port 2. So this is what our feedback network looks like. All right, so what's R11 going to be? What do we do? Look into port 1 with port 2 short circuited. So it's RF. What's R22 going to do? We look into 2 with port 1 short circuited, so it's also RF. To figure out K, recall that we apply a voltage here at port 2 called V out, short circuit port 1, and we're looking for the current IF for this direction. So I flowing this way, I guess that would be counterclockwise around the loop, would simply be V out over RF. We want the current going the other way, so it's negative V out over RF. So I out so we have IF over V out is negative V out over RF divided by V out is -1 over RF. That's our feedback factor. Notice here that our feedback factor is inherently a negative quantity, which means our expectation here is that our open loop gain needs to be a negative quantity as well. Otherwise, we will accidentally have positive feedback system. Okay. So how do we feel about the analysis of what our feedback system contributes to the loading of our open loop amplifier? Anything seem wild, crazy, or not making sense based on the parameters that we've developed? Great. All right, so our open loop amplifier circuit is going to look something like this. Actually, let me scooch that over a smidge. So here is RD1. Here's our DC bias voltage. Here is our current IN. And here is where R11 is being applied, where we're recognizing that R11 is simply RF. Looks like I gave myself a little bit too much room up here at the top, but it'll be okay. So here's RD2. Here's where R22 is applied. This is also simply RF. So let's call this guy M1 and this guy M2. We're going to break this up into stages, more easily figure out what exactly is going on here. I'm going to call this voltage Vy, this voltage Vx, and so my overall gain A should look something like V out over Vy times Vy over Vx times Vx over I. Yeah. Anything seem unreasonable about that? So really just this first simple stage converts our input signal into a voltage, and then we have a voltage amplifier and a voltage amplifier. All right, so let's start with the Vx over In portion. Anybody have any thoughts? Very close. But You're neglecting the fact that this small signal current will also see a resistance looking in to the source of that transistor. So instead of just being RF, it'll be RF in parallel with 1 over GM. All right. From Vx to Vy, what do we have? Let's say that we're not particularly concerned about channel length modulation to make our lives a little easier. So our input voltage is being applied at the source. Our output voltage is being taken at the drain. So that's a common gate amplifier. Common gate doesn't have a negative sign out front. Positive GMRD. So GM1, RD1. And then we'll have V out over Vy. So effectively, our input voltage Vy is applied at the gate of transistor M2. Our output voltage is taken at the drain of transistor M2. So that is a common source amplifier. We don't have source degeneration, but we do have a loading impedance here, RF, that we need to take into account. So channel length modulation neglected. What do we see to the right of the red dashed line? Exactly right. Negative GM2 times RD2 in parallel with RF. Multiply these three things together, we get our our open loop gain. And we do have a negative open loop gain, so we do have negative feedback since our feedback factor K is also a negative quantity. Okay. So A, let's see, we're going to have negative GM1, GM2, RD1, RF in parallel with 1 over GM, RD2 in parallel with RF. Probably play around with this algebraically and cancel things out. I'm not going to bother with it for now. Literally direct multiplication, and let's call it a day then. All right. We need to calculate RI and RO as well. So what's RI? Well, we already figured it out. It's RF in parallel with 1 over GM. What's RO? RD2 in parallel with RF. And at this point, we literally just plug these results in to these three equations and our analysis is done. So that is a feedback trans resistance amplifier. Okay? Any questions, comments, or concerns regarding our analysis here? All right, hopefully this crap is seeming like old hat, because at this point, I believe we've beat most of these concepts to death. It's just looking at the nuances between how we look at our feedback. So our last amplifier that we need to look at then is the feedback current. So I will start with our open loop amplifier. Which is largely the same thing every time. On the input side, we have some resistance Ri, over which we have a voltage drop Vi and a current II flowing. Since this is a current amplifier, we're going to have A times II for our dependent source. Here's our output resistance R0. And getting slightly ahead of myself here, our quantity of interest is this current I out. I'm going to put a box around this. All right, so our feedback network in this case should be connected in parallel to the input side of the amplifier because we're mixing currents, and it should be connected in series at the output side because we are sensing current. So that's going to look something like this. So here is our ideal feedback network. All right, so on the output side of our open loop amplifier, our connection is going to look something like this. We look in through here. That's how we see ROF. On the input side, we have a parallel connection. Here's our feedback current IF. And then because this is a current amplifier, our input signal will be some current I sig, like so. Looking in through here is where we see RIF. And without derivation, because this is a feedback amplifier, we know that AF should be A over 1 plus KA, because our feedback network is connected to the input side of our open loop amplifier. We should see that our input resistance goes down. So we'll have Ri over 1 plus Ka. And on the output side, since we have a series connection, that's going to boost the resistance such that we'll have Ro times 1 plus Ka. To determine our loading parameters, get R1. Here's our feedback network. Port 1, port 2. We're going to look in port 1 with port 2 open circuited to calculate R22. We look at our feedback network. We look in through port 2 with port 1 short circuited. And then finally, to determine our feedback factor K, we take our feedback network and we're going to apply the current source to port 2. I'm going to call I out. We're going to measure the response at port 1 under the constraint that V1 is 0, such that K will be equal to IF over I out when the voltage drop across port 1 is 0 volts. It should be fairly obvious that we're going to wind up having negative values for K in this case as well, because they both wind up flowing in the same. All right. So our example problem. Let's say that we have something like this. This guy RD. Here we have some resistor R1. Here we have some resistor R2. Here is ISIG. Here's IF. Here's II. Now, one thing that I want to point out here, and this is something that Race and I were kind of discussing at the end of the last class. Effectively, if this signal resistance, or excuse me, signal source here were a practical signal source, we could do a source transformation, and this would now look like a feedback transconductance amplifier, right? So the reason why I'm bringing that up is because we have this quantity II right here, which is flowing into the gate of this transistor, which we know intuitively shouldn't actually be doing anything. What's actually happening is the voltage at this node is floating. which is causing our feedback effect to happen. Right? So our output current in some way, shape, or form influences the amount of current that's flowing through resistor R1, which in turn gets subtracted from this I sig quantity. The only other path I1 really, or II has to take is up through there. So what in truth is happening is the voltage at this node is moving up and down depending on what our input current is, and that's where our actual feedback is going through. But I'm trying to force this square peg into the round hole that we've developed. Look. Pardon? So yeah. So, but the error current should approximately be 0 if our amplifier is an ideal amplifier anyway. The whole point of these feedback things, as you get closer to ideal, your gain is determined entirely by the ratio of the resistances. And this signal should be approximately 0 either way. I'm just trying to explain to you guys what's actually happening in the circuit, because if we looked at this, we should say that II is 0 right off the bat because it's the current that's flowing into an open circuit. I'm just trying to explain the processes as to why this actually meets the definition of a negative feedback circuit. Okay. So let me label some things here real quick. This is where we're going to look in to determine RIF. This is where we're going to look in to determine our OF, our feedback network. Something's tickling my nose. Is going to look like this. Here's resistor R1. Here's resistor R2. This is port 1. This is port 2. So R11, we look in through port 1 with port 2 open circuited. We see R1 plus R2. For R22, we look in through port 2 with port 1 short circuited. So we see R1 in parallel with R22. And to determine our feedback factor K, we apply current source here, I out, look for the current here. Sorry, I shouldn't have a source here. Like so. And using current division, this is going to be negative R2 over R1 plus R2. Everybody okay with that? I'm using the current division when there are only 2 resistances, so I'm not using the reciprocal definition there. All righty. So our open loop circuit is going to look something like this. Here's R11. Here is I in. Here is R22. Call this guy M1, this guy M2. Here where we look in to find Ri. Here's where we look in to find RO, sorry, not with an F. And we can effectively break this into two stages. So let's see, let's call this Vy, this Vx, and overall we're going to have I out over Vy multiplied by Vy over Vx multiplied by Vx over In. What's Vx over In? So just R1 way. Yep. Because when we look into the input terminal at the gate there, we see an open circuit. So just R1 way. Vy over Vx. Channel length modulation neglected, just for the sake of ease. GM1RD, absolutely right. And then for I out over Vy, this is extraordinarily similar. And by that, I mean, why does my thing keep moving out of the way when I try to write something down? That's what we did. Yes. Oh, yes, very much. Thank you. Negative GMRD because we have a common source amplifier. And we'd find out that our gain wouldn't work out correctly if we didn't do that. So thank you for that catch. Or we'd wind up with positive feedback and we didn't notice that. All right. So we're going to figure this bit out the lazy man's way. And what I mean by that very specifically is we know that this transistor is converting this voltage Vy into the output current by a factor of Gm times VGS, right? So we're going to have I out is equal to GM2 times VGS. Well, VG in this case is Vy. Vs in this case is I out times R22. So that means we're going to have I out times 1 plus GM R22 is equal to GM2 Vy. And from this, I out over Vy is GM2 over 1 plus GM2 R22. Anything seem unreasonable about that method as opposed to drawing the small signal model of getting literally the exact same result? Multiplying these three things together, A is negative GM1, GM2, RD R11 over 1 plus GM2 R22. What's RI? R11. RO. So this is going to be a little bit wonky looking, and the reason why I say that specifically is it's going to look weird because we are not including channel length modulation, right? If we were including channel length modulation, it would be R02 generated by R22. So that would look like R02 plus R22 plus GM2 R02 R22. Okay. But because we don't have, we're not including the effects of channel length modulation. What does it look like when we look into the drain of a transistor? Let's look. Take a quick peek here, right? So our gate should be a short circuit, or it should be grounded. Here we have VGS2. Down here we have that resistance R22. Here's GM2, VGS2. And here's where we're looking in, right? We're breaking in and looking down. So if we put a test source here, V test, put a line down here just so we can, I think this will be enough space to do this now, right? So VGS is 0 minus IX times R22. I want to say, Jordan, this is something that we looked at much earlier this quarter, or maybe it was last quarter where everything wound up being 0, but I'm just going to double check here. This looks familiar, but I don't exactly recall how it's supposed to work out. So IX is equal to GM2 times VGS, which is negative IX R22. If GM2 and R22 aren't 0, then the only way that this works out is when IX is 0. Is that? Yeah. Which means R naught is infinity. So effectively, we see an open circuit looking down. If we didn't have, or if we included the effects of channel length modulation, there would be that path R naught to here. And we would have the simple look of R naught 2 being degenerated by R22, which again would just be R22 plus R naught 2 plus GM2 R naught 2 R22.